comes from the academia. Thank you. And this paper is coming really from some top academics, and its main goal is to provide trustworthy evidence of runtime integrity to complement the boot time and load time attestation. And this was intended.
Sorry. I'm so sorry.
Oh.
I am so sorry.
I got it. All right, so this first proposal was exactly intended to cover these return-oriented or jump-oriented programming attacks, and the main question that they were trying to ask was how to get evidence of runtime integrity in face of such attacks. So how does this work? I'm talking about the PowerPoint presentation. So. Yeah, so this proposal targets simple embedded software for bare metal devices, and it uses ARM trust zone as a root of trust. So practically, they put some sort of monitoring component that is recording every extension. I will actually show it in a moment, but practically it's trying to complement the control flow integrity techniques that are trying to enforce a certain control flow integrity, which are stateless and context unaware, and that cannot provide attestation. So they try to provide this trustworthy evidence. How does it work? It works by instrumenting the application to report control transfer events at each control transfer instruction. This means that once the program execution moves from one node to another, such as in this short animation, every transition is recorded, and a buffer in this trusted execution environment is filled. And when the buffer is full, it sends all these collected paths to a verifier in order to see if the program took a legitimate path. And this approach incurs high runtime overhead because, of course, monitoring every single transaction means a huge impact on the performance of the prover. High network overhead, it transfers a lot of events, of course, and also it kind of assumes a mythical verifier that can just understand what every program everywhere is doing or should be doing, and ideally could also monitor many devices at the same time. And this is actually not scalable and not practical. It also doesn't offer any particular deterministic verification method. This solution was designed for very simple embedded devices, such as an insulin pump, which has maybe a couple of loops. So it's not really suitable for complex software stacks. And also this anchoring in a TE as a root of trust, we don't find as the choice that we would make. So this was the seminal work. Based on it, there is quite a large number of papers. These are just the more famous ones that try to address some of the limitation of the original work. Each of them has some links, so when I will share the slides, you can get read about each of them, and you see them organized based on which one require hardware modification or which ones try to do it in software. And however, they all have one or more limitations, such as either they're intrusive, expensive, just like C-flat, non-scalable or not practical for various reasons. So we have a small table here that tries to compare the most important of these research papers, and what we see is that many of them require hardware modification. None of them is really scalable to complex software, and is not scalable actually to many provers under a certain verifier, but also only one is suitable for complex software. However, you see that the overhead of that solution is actually high, so it's not acceptable for practical devices. In terms of assumptions or requirements that they have from the platform, you see that they go from simple bare metal software, so no hard requirement. However, some of the more advanced ones, they require hardware extensions and correct implementation of the hardware, and also some newer hardware capabilities such as memory tagging. In terms of roots of trust, none of them uses one of the TCG roots of trust. So what should be the next step for runtime attestation, in our opinion? So we have a significant threat. We have requirements from customers that are interested in trustworthy evidence. And also we have a number of defenses that don't suit our needs. So we want to think of more practical approaches. And our proposal that we have been researching in the last couple of years is called CFA Plus. And it's a control flow attestation technique that relies on recent extensions that we find in ARM CPUs, but which we find also on other architectures today under slightly different names, but similar behavior. So what does this technology try to do? It tries to enforce the control flow of the program to behave according to a legitimate calling graph. And this calling graph is established at function level. That means that the path that is followed when forwarding or when invoking functions, when doing calls, must be the same when we return. It's quite a simple concept. If you go on one path, return on the same. And this is how this would look. Let's assume that we would do a call and we arrive into some node. When we return, a good program will return on the same path. Now, if an attacker would like to hijack the control flow, it would need to introduce some new forward edges, which is difficult but possible. This would be a jump-oriented programming attack. However, the scheme will detect the attack on the return path. So when the new edge was introduced, the return path will still be different because if we introduce a jump, an edge on the forward path, the function at which we jump will only return from to its original address. So we will detect this on the return path. Also, the paths are identified per call site and not just per function. So we have a more finely granular solution than existing CFI solutions that are deployed in the compilers or that we've seen in the academia. So yeah, I forgot why we had this one as well. I think this one is showing the return path detection. So yeah, so again, a program that takes the returns to the wrong part. So what happens if a violation occurs? Well, we will trigger an exception handler that is in a kernel, and it will log errors and anchor them in a root of trust. The technology has three pillars. The first one is a selective instrumentation of the call instructions. So we we encode and decode two reserved registers using a XOR instruction in each call site. I won't go into the technical details too much, so that let's say I try not to make it too difficult to follow. However, why we do this is because it helps us to implicitly monitor the execution of this scheme, unlike other explicit control flow attestation mechanisms which just log the edges. So with these registers, we practically introduce a unique context-sensitive ID for each edge that then we can recognize when we do the verification. The second pillar of CFA Plus is to instrument or to authenticate return instructions. The current solution we use is to use some hard-coded jump tables. So from a function, you can only jump to a certain set of addresses. However, we have also other solutions that could use pointer authentication, for example, to make sure that we only return to the right place. And this helps us to protect backward edges and to detect the misuse of forward edges. The last part is this ARM technology that we mentioned. It's called branch target indirection. It is serving to enforce compliance with an instrumentation policy, and it works by introducing some landing pads so that practically when a jump is happening, or so an indirect call or indirect jump is happening, then the jump can be done only at the address that is marked by the landing pad. And this helps us actually enforce the software instrumentation. The solution could work in theory only in software as well, but it helps us to enforce the policy, and also it adds the prevention capabilities. It means that when a particular violation would happen, the BTI would crash the program, so it wouldn't allow it to run compromised. The overall architecture of this technology is starting with the compiler toolchain. So we have a CFA Plus plugin for LLVM, and that allows us from the source code to add additional instrumentation that I showed you. And then once we deploy the binary on an actual device, which we see on, maybe I use the laser. So this is the actual device. And you see here that we have an exception handler. It's a kernel module that is the one intercepting the violations and logging violations in a log that is anchored to the root of trust. And we have an attestation agent that can report. It can either by itself notify a verifier in case a violation occurs, or it can provide the log whenever a verifier requests it. And this practically just requires the root of trust and the modern CPUs that have this BTI extension. In terms of the attestation service architecture, we have a solution that uses the noise framework for security protocols, but mainly the idea is that we have a traditional enrollment of a TPM with a signing key and with an attestation key, and practically we just do quotes from the TPM. The TPM provides the quote. We can verify the integrity of the runtime log, and we can decide if something has happened. So when a BTI violation has happened, what we will see is that we will receive a quote with an event, which practically shows that there is a new event. And whenever a program runs correctly, there is no violation, there will be nothing in this log. When there is a violation, there would be a log entry, and this is how the log would look like. You would have the command that triggered the violation, so the launch command of a particular process, its ID, and then the value of these two registers that we define, that we reserve specifically for the scheme to help with further forensics. And we can have a log that the system can that can be used by the agent that can be used by the kernel module to log violations in different types, so in different processes. And the log will mainly contain for each application, for the instance of each application, only one event, that is the violation. This is how a log would look like. So quite basic. There is an event, and then the command, as I mentioned, the process ID and the values of the registers. So I don't go into the details of this because probably we don't have the time. There is a paper submitted. We hope that it will be accepted soon at a conference, and then we can provide also the paper. I would like to just look briefly at what we achieved with this solution. So in our opinion, this is an efficient, implicit, and inline monitoring scheme. So it doesn't depend on a trust zone or another trust execution environment to keep monitoring the software. The instrumentation is in line, and it's let's say the performance impact that we have measured is actually quite low. And this means that the program doesn't need an additional component to just monitor its execution. It offers some minimal sign reports. It offers prevention capabilities. As I said, in case of violations, it can just kill the program. And we believe it's scalable because of these minimal sign reports and because of the efficiency implications. It's data scarce, meaning we don't transfer a lot of information on the network, and it's ROT anchored. For now, we use the TPM. We could use a DICE protection environment or any other type of root of trust that can provide reporting. Its downsides are that, of course, it won't work with legacy systems that don't have these hardware extensions, but we think it is cross-architecture conceptually. And we do have some binary size overhead. Pretty much the binary of the instrumented binary is almost 2 times bigger. However, this is a sort of memory to performance trade-off that we are considering reasonable. Also, we need to reserve these 2 registers. So these registers will not be used by the compiler for other programs to avoid spilling the values of the registers, which are used as part of the scheme. So with this, I would like to just say a few words about what we learned from this and why we are bringing this to the TCG today. So first of all, for efficiency purposes, as you see, we only record violations. That means it's not a benign, it's a malign integrity evidence. It's an integrity evidence that the integrity has been tampered. And this is different from the usual approach that we do in attestation, which is trust what you recognize. However, that's because we have so far not found any efficient benign integrity evidence for the runtime. Also, we currently use a custom log format, but we would be interested to see if the experts in TCG that work on the canonical event log format or on other related initiatives would see this as an opportunity to try to define some space for such events. Also, we do have some analysis, but I think we don't have a clear decision on what parts of the system would benefit the most from runtime attestation. Either we would apply it to critical applications, components from the system TCB, runtime firmware. We could also consider applying it to discrete roots of trust that would have a similar capability. In fact, on the latest microcontroller course, there is a equivalent ISA extension, or why not to resilience engines that are responsible for security in the system. So that's the summary of our presentation. Apologies if it was a bit long. We would love to hear what you think about this, if you think it's valuable or not at all. And if you worked on similar concepts, I would be glad to hear from you. Thank you.
We have time for about one question. So if you have a burning question, you have to ask right this second.
This got the priority here. I'll tell you, have you compared, you mentioned critical applications, compared the memory size and any performance hits over kind of a general purpose set of applications, PDF files, versus a more constrained, dedicated application like a PLC or an IPC that has a very limited set but are very critical applications. It seems having that's a high contrast, those would be your first targets, I would think. But sure, what's the range of memory hit and performance hit?
I would say performance hit, we are somewhere around 4 to 10%, depending on types of application, which is in some cases maybe like 5 times lower than the next such solution. In terms of memory overhead, it depends, of course, on what kind of programs. If I remember correctly, it's up to 100%. In some cases, it could be lower. And when we don't use these hard-coded jump tables, we actually reduce a lot the performance impact. But for that, we need to use another instruction from ARM CPU's pointer authentication. So that's a further development.
Okay.